Welcome, everybody. It is our immense pleasure to host the second edition of Formula Uzi 2022, a student AI-based autonomous car racing competition. And it's safe to say it is the only one of this kind in Switzerland. So if you want to organize an event of this kind, there is a number of people which is involved. And first and foremost, I want to thank our sponsors. The Software Institute in Premis of the Università Svizzera Italiana, Hassler Stiftung, Banana.ch, and DXT Commodities. Behind this kind of event, there is always people. And I would like to call here all the people who helped with great work, especially during this week. Like, they did a monumental work to organize everything that you see today and tonight. So please welcome our organization team: Matteo, Vincenzo, Roberto, Andrea, who cannot be here today, Valentina, Mauro, Michele. And there are, of course, many more who helped, like, also from the SUPSI side to set up this very room today. They will probably be here tomorrow and on Sunday, so you'll see them around with this t-shirt. So let's thank them again. So I wanted to step back a little and tell you about why we did Formula Uzi. And basically, it all started with a master thesis, believe it or not. There was this man, Brian Pulfer, who did the thesis with me, and it was crazy enough to embark in one of the most difficult theses back then, which is testing autonomous driving system in a real environment, in a physical domain, using a small-scale car. So here in the slide, you can see like his first efforts, like trying to set up the car. Of course, there were funny things happening. But then we immediately realized that it was something that we wanted to share with the students here. Of course, again, if you want to embark this effort, you need people. So the second people I contacted after Brian was actually Mauro. And Mauro is our reference person here at Uzi for this kind of events and many other things. So I basically approached him, like saying, hey, we have this cool thing, we have to do something with the students. It was like, you don't have to do what? And then, like, over the months, we tried to devise, how this competition could be. And so we did it. We did the first edition last year. It was, again, a gigantic effort by the team, but it was absolutely worth it. That's why we wanted to repeat it one more time. Just to give you a little numbers, last year we had one challenge, the lane keeping challenge. There were 32 participants, and the amount of prizes was around 5K. This year we wanted to go bigger. So we devised one more challenge for you to have fun, many more participants, and much more money for you to win. So at the end of the day, like, we had the challenge in which we are asking you to compete one against another. In the first challenge, it's a lane keeping. It's something that we already did last year. So basically what we are asking you to do is to teach an AI algorithm how to drive. And this year you can use whatever framework, whatever technique, whatever software you want, both supervised and reinforcement. The training tracks are gonna be two, one more with respect to last year. So behind you there is one, and we are gonna add another one later in the night. So the way we see it, like, one of the problems that was last year is that the access to the training track was only one team at a time. So there were 9 teams, like, waiting for their turn. So we double it. We use 2 tracks as training, so you can work 2 teams in parallel. And basically, you're gonna use this training track today and Saturday for collecting your data. Because starting tomorrow evening and Sunday morning, we're going to have the first races for what concerns the lane keeping challenge. And the way it is organized, it's like you're going to have a testing tracks which is unknown at training time in a pure machine learning style. You're going to have 3 heats in which you can compete, start trying to do as many autonomous laps as you can. And what counts here is the time. So the faster the car goes, the better. For the head-to-head challenge, we actually made our own racing track. It was a bit like hard to devise something that was sufficiently wide for hosting 2 cars. So we made it our own. It's on the other room. You can inspect it whenever you want. It's 2 meters wide, so you can host like 2 cars for racing one against the other. And this track is going to be both for training and testing. Okay, so no surprises incoming. But at the end of the day, the main prizes, the main challenge is going to be the head-to-head challenge. So the biggest like prize amount is going to be for this second challenge. A bit of a program. So today, after this opening, we have 2 fantastic keynotes by the speaker who are like sit here next to me, followed by an apéro. And then, I mean, the hackathon starts officially, so you can start already doing your magic. Tomorrow, basically, is the day devoted to, your work. But we want to finish already with a race, with a lane keeping race, and taking like official timings, just to give you yourself like a feeling about how your algorithm have learned so far. So you can eventually like spend some more time during the night to refine them. Of course, we can have a break. We're gonna have a break with the pizza night. But the way we see it, like Sunday morning, we do 1 more race for the lane keeping challenge. So eventually you can refine your models. At 10, we are going to have the head-to-head tournament. We're going to share additional details about how this competition goes, because it's a bit lengthy and it's not good for an opening. But basically, we want to end all the races by midday. So we end with the award ceremony and with the standing lunch together. I'm aware that most of you were asking for this information, so you can feel free to use the Formula Uzi like hotspot that we created for you, but just try not to abuse it, because all the cars are set to work with this environment. So like if you're an Uzi student, feel free to use the typical Uzi account for this. So what you received is basically a donkey car kit, which is a small-scale self-driving car. As opposed to last year, in which we asked the participant to assemble it, this year we decided to assemble it for you and to test it. So basically, the competition is flat from the very beginning. What counts here is software. Plus, we have some additional equipment to connect with the Jetson Nano, like a monitor, mouse, and some other utilities. Very few rules. I mean, it's a software competition, so no hardware modification to make the car go faster. So what counts is software. Solution must be based on artificial intelligence. That's safe to say. Basically, all the data and the models must be delivered by us. And try, please, not to walk on the racetrack with the shoes, because they are extremely expensive. Without further ado, I think I want to introduce you with the 2 keynote speakers for tonight. First is going to be Marco Coppini, which is the opposite of the slide here. We just decided to swap the order because it just makes sense, right? Marco is a Formula 3 driver and an expert in driving simulators, so he's going to share us his experience, his immense experience, I would say, because he was telling me stories and it was just fascinating to hear them. And Marco's talk is going to be followed by Matteo's, who is a professor at the Politecnico di Milano, And what basically we are trying to do here at the small scale, it does it at full scale, with real scale cars. So again, perhaps it's gonna share with you some intuition about how to win this kind of competitions, because he did it. So, Marco, please, you can stand back.
So, thank you all for inviting me to this event, and I'm really honored to be here because I was not ready to take such nice event into my experience of driver, of analogic driver who got into the digital driving, and then I became even the Dallara guy in Switzerland. So I have some experience to transfer to you because Dallara is a serious player in the new technology in the automotive sector. Mm-hmm. So I will tell you something. I will tell you something about my experience, my empirical experience that turns the digital knowledge into analogic driving. Allora, I got since 15 years driving on tracks with GTs, racing, and 5 years ago I started to race with Formula, which are open wheels, and this is totally different game because with open wheels you have problems with aerodynamics, with weight, with different speed of cornering and so on. And then there is an issue with the lines, the circuits, because just to give you an example, I was driving this year in Zandvoort on the new configuration, so I'm not a professional team like the great guy, and I was learning the Zandvoort new configuration circuit on digital simulators. So I was able to find a good guy who was able to modelize my own car into a software, and we were using Assetto Corsa. Maybe someone knows. Okay, because the two main software are iRacing and Assetto Corsa. iRacing is a closed resource, while Assetto Corsa is open. So you can add your own car, you can add different circuits with developments and updates. So I was experiencing driving in Zandvoort a lot, day and nights before going there, and when I was there, I was ready. That can be a serious challenge because you remember many years ago with GT5, there was a young guy who won the world challenge of GT5, and then he went to the Nordschleife and in Flugplatz, which is a place where the car lose the front, the car took air under the body, no, and the car was totally flying out of the circuits with great damage. So yes, the digital experience is important to learn, but then you have to drive. With this growing experience, you can learn a lot even in circuits where you can never be. I mentioned you some circuit, Pau. It is written P-A-U, Pau. It is in the deep France, close to Lourdes. And it's a beautiful city circuit, but you cannot exercise because it's a city. So you cannot use it on normal time. You cannot train. So you have to use the digital experience. Great. I wish you all to learn and drive because you will apply your theoretical models into real analogic driving. But I was even growing with Dallara because they have an incredible simulator in Varano, and they are investing a lot of money into simulating technology and software, because they said, okay, how can we develop, who of you knows Dallara, the name Dallara? Okay, some, but just a few. Nobody knows. Every weekend, 300 Dallaras are racing on circuits, no? And most all of them are on the podium. Dallara is the Indy car, which, and I think Matteo then will talk to you about the Indy Light, which was used in the autonomous driving experience. IndyCar, Super Formula, which is the Formula 1 in Japan, Formula 3, Formula 4, all the, you remember all the hypercars, LMP1, LMP2, the new version of the LMDH, which will be delivered in the new WEC competition in Le Mans, will be Dallara. The frame and the body frame is Dallara. Technology of aerodynamics is Dallara. And how can they develop Bugatti, Porsche hypercar, Ferrari, Maserati? How can they develop without crashing, without wasting money? They have to develop software. So what you are doing now is something that great factory are using for the future, because using simulation, they are able to perform a car which fits the needs without crashing, without killing pilots, because this is the risk, without huge waste of money, because every model costs millions, no? So their approach is, we have a great simulator, 15 million euro of costs, and every year around 1 million of updating the software and the actuators, sensors, and so on. Why? Because they model the car before. They put the model on the simulator. They call Leclerc or Bottas or whoever, or Giovinazzi, to test the car. They use the car on tracks with the simulation of humidity, temperature, pressure of tires, everything. Everything is a parameter. So they test the car. The pilot gives back the experience, the impression. They perform another model, then another simulation, and if the car performs, they realize a 1x2 model of the car, and they put the car into the wing gallery. In the wing gallery, they test, because they have a tapis roulant, no? Come si dice? Treadmill. Okay, there is a treadmill. So there is the wing, but there is even the treadmill who simulate the correct pressure of aerodynamics and fluidodynamics with real effect, because the car is not only the wing, is even moving back and forth laterally, and so if the car is good, they go to production, the real model. Or they change the simulation, they bring back to the simulator, so there is a process made of computer design, simulating, realizing the model, testing the model in the wing gallery, and then back. After all this story, they realize a model who performs to be the Indy car or the Indy Light, and their approach is so put forward in the technology that they understood that after 10 years of investments, billions and billions of money just to go parking the car, because autonomous driving now, can you imagine Tesla, Google, Apple, they park the car, okay, they go from point A, point B if Google is working, Google Maps is working, so they apply rules, yes, but in a normal environment without variability. But the real challenge is variability. So the problem is speed, variability, which means volatility of conditions, not predictable in environment. And they invested in this challenge 2 years ago, which was the IndyCar Autonomous Challenge, no? And in 1 year, they said, okay, if we have to invest and spend some money with 20, 40, 50 teams working on the modeling, it will cost a lot of money. But if we put a price on who will perform better, like you will do probably tomorrow or after tomorrow, we put the price, okay, and they put a price of $1 million. They had 40 applications of 40 universities, and Polytechnic of Milano was one of them winning, successful. To do what with these 40? To improve the capacity so quick, so fast, that in 1 year they were able to reach level of performance never seen. Not only for maximum speed, but even for driving on track, high speed, and challenge each other. It was not a final test. It takes here and there, probably. But the result, for now, are really very, 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 very good, very good. And what they say, autonomous drive is not, has not the objective of compare human to machine, no. Or to enjoy the autonomous racing, because, okay, who win? The model, maybe. But the real challenge is improve our capabilities. They are studying how to implement the modeling with shadow cars, shadow lines into helmets, on the screen of helmet. They are studying how to put the track and the shadow perfect line of driving, which you improve, because there is the theoretical perfect line, and then there is your line, and then there is your best line. And then you can follow your best or improve it to follow. So the autonomous drive becomes a mean of improving our knowledge. So Dallara is in this field with probably 500 engineers, average age around 30 years old, from everywhere. And they have one big event like in Varano on track with 3,500 people coming from all the world, all university, testing their own cars. They have parameters of different weight, power, and so on. Because in the Dallara world, technology belongs to young people, to people who has no limits of developments, because they don't know what is impossible. I'm old, so I think something is impossible. But a young guy doesn't know that this is impossible, so they always try to go beyond. So I want to transfer you this experience, because, and if you will like, I could even organize something to go there and have some meeting, and because this culture has to be transferred to people who is looking for technology, because you are not doing something. I see big factories. Porsche is there, Maserati is there, Ferrari is there. They are not developing because Dallara is the company devoted to develop the technology. So I wanna tell you, you are on the right way, because there is not so many people, and your experience even with the Politecnico was very important in the autonomous drive, because Dallara was telling, okay, I put 1 million price, and then to the winner, 10 teams, probably, it was, no, 10 teams. I give you a Indy Light car. Indy Light is the smaller racing car of the Indy Formula, Indy cars, who runs up to 300 kilometers. And they just put sensors and actuators. Sensor to check everything, no? So they said, okay, this is the hardware. The software belongs to the developers. So they gave just the frame, no, the structure, the hardware of the machine. everything else was realized by the software. And finally, it was absolutely incredible to watch these cars running by night, because you say, okay, they don't need lights, they don't need nothing. Okay, they need great connections, because even Cisco was a great player, because, okay, you have Wi-Fi here, and I wish it will work properly. But to race in Indianapolis, they need Cisco, and they need a connection working, how fast, I don't know, you are the expert, so. But you are on the right track, because all the great factories are working on these issues. And okay, I was surprised when Andrea invited me, because I'm not a software guy, I'm not a professor. Okay, I drive cars, I race with cars, I know where the challenges are, and I will be here Sunday morning, because I will enjoy to watch your jobs. But I wish we will do something better next year, even next year. I don't know, Andrea, if the time is good or not. I have still 5 minutes or not? Okay. Just to tell you that in the world of Dallara, there are such technology in terms of aerodynamics, because probably you saw some great crash last year from Grosjean when he went into the barriers and the car took, no? It was a Dallara. When Sofia Florsch was flying against the grid at 270 kilometers, the car was a Dallara. So Dallara was developing a concept of carbon fiber frame of the car to give maximum safety to the drivers, and now they are developing the autonomous driving. So I think, okay, but why these guys are working on safety of cars, safety of driving, no? Probably because the great corporations are looking to be there. They are not looking, okay, then everybody, I'm a pilot of analogic cars, so I will use analogic big time. But when I have to make commuting between a point A and B, I don't need to drive the car. I don't need to drive to go to Zurich. I don't need it. If I have to enjoy driving, okay, I go on track, or I go on the hills driving my Dallara Stradale, which is a beautiful car, but it is important that the focus of the biggest factory, and I mean the serious biggest, no? Ferrari, Porsche, Maserati, McLaren, Lamborghini are there. And I think all the efforts from the big investments they are making are in this direction, are not in speed. In my experience, I see Dallara Stradale, okay, then I became, because I love these guys, and you understood it, I became the importer of Dallara Stradale in Switzerland, and the only pleasure is that people who drive the Dallara say, okay, but what is this car? It's crazy, because it weighs 800 kilos, and it has a downforce of 800 kilos. So it can go on the roof of this room, no, because the downforce is close to the weight. Nobody knew what is downforce. Nobody knew what was aerodynamic efficiency. Aerodynamic efficiency of Dallara Stradale, which is a street legal car, is 2.5. Of Lamborghini Huracan is 1.3. Take this like, okay, just an indication. But all the parameters we are working on are in this direction. So I don't know if you are just software guy applying models and software, or you are car enthusiasts. I don't know, no? Or both. No? In any case, I can tell you, I will enjoy to bring you a team, the winner. Let's put this on the price of a team, the 3 team winners. I will try to organize a meeting, a day, a factory tour in Varano, no? Because, by the way, they were making this university, I was explaining to Andrea, which is named MUNER. MUNER stands for Motor Vehicles University of Emilia-Romagna, which is very Italian name. It is very, but the target was to merge different factories, competitors, serious, heavy competitors, Lamborghini with Ferrari, can you imagine? Maserati, Pagani, Dallara, Haas, Magneti Marelli, Ducati, and other 2, I don't remember. And so they put all these factory together to develop a post-laurea, a PhD in engineer applied to motor vehicles. Because they said, okay, but we know how to make the car, we have the culture, we have the history, we have the results, so why young guy from Italy, they go to Detroit? Why? Or Indianapolis? We attract people here because they will bring the tradition and technology abroad. So they were developing this concept in Dallara Academy of this Muner University, where you can have the software field, the software branch, or the aerodynamics, or the frame and the carbon fiber technology. And I think it's a beautiful example of integrating university with culture of factory. Adesso Matteo will take place now, and he will explain you what was the experience with the autonomous drive in probably in Las Vegas or where?
A little bit of everything. So we will start with Las Vegas, and from there we will move on.
Okay, and these cars were from Dallara world. So to me, it was a great opportunity to talk to you about the name of a company which is almost totally unknown to real world. Okay, so thank you very much, and sorry for waiting.
I'm totally down for the prize. What do you think? As long as you bring the organization team as well, not only who wins. Okay, fine. I was curious about how you use the trajectories by the software, by the autopilots, to train yourself, to train your skills. So who trains the autopilot first? Is it another driver? Is it fully autonomous?
Usually the lines are self-provided by the model,
Okay.
but then you remove it completely, and then when you realize your best laps, your best performance, you put again the lines to check if you respect or not. But usually the lines are not specialized for your own car. So the lines are made in general terms, but can you imagine the behavior of a Formula 3 is totally different from behavior of a Formula 1 or a GT car. So point of braking, point of apex, point of exit of the curve are totally different, no? But it's important for you because they give you the ideal line. And this, I think it will be incredible when they will be able to implement the helmet projection, no, of the shadow car or shadow line, because it will be totally crazy. Can you imagine? You drive and you drive on real time with the line on track. And it can be dangerous because we can do it even on road, no? On public legal road, and to perform better. Okay, on legal road, if the police find you with the helmet, probably you have some issues, but the future is there. And now, even great pilot, I mean, Leclerc, I met Leclerc in Varano, he was testing, even Bottas, Giovinazzi, and they're working on this stuff. So you say, but what is the key point? Is the software now? Is the technology? Or is the driver? There is no more such difference, no? It's an incredible integration. I saw a week ago Verstappen racing on the WEC new car in Le Mans. And they said, this is the Formula One toppest pilot, and he enjoyed driving on a simulator. Okay, I recommend you. I was not able to drive on the simulator of Dallara, and I sent some picture of, because this is a kind of structure in the middle of, with 4 actuators, no, 5 meters from the, and it is very, 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 I was feeling very sick, very ill, because of reaction between the actuators of the computer and my own. Young people is not suffering, but myself, yes, I do. So I was not able to perform on this simulator. It's seriously sucking. But
I think I can afford one more question for Marco. Anything from the audience? Come on, guys.
So good luck to the teams, and I will enjoy to bring you to Varano.
Thank you again. You're great. Oh, we actually had a question, right? Oh, yeah. We can afford it. I think Marco can take it, right?
No, I just want to ask you, since you said several times that this is like young people's business, but you also remarked that you're not so young anymore.
Not at all.
But then I guess you must be bringing something. I mean, experience must also be important. And so, what's your specific contributions? Why of people with more experience?
Listen, I don't know, because once, Mr. Dallara Giampaolo, who is a serious, great visionary guy, serious, he said, I like young people because they don't know what is impossible, first. And so they don't know where they have to stop it, because they challenge, because they have no limits. So my contribution, or the old school contribution to where it lies. Why? Because in the past there was no software, there was no technology. I mean, cars were not digital. Now a car has electric steering, brake electric, ABS, everything is, no? While in the past, there was nothing. Allora, I drive this car, crazy cars, Formula 1 and Formula 3, which is totally analogic. So I have the clutch, 5 gear, and you don't need electronic. Now, you see the guys in Formula 1. It is everything is electronics. They have, I mean, in boxes, they have all the telemetry. Telemetry is crazy, you can imagine. The power of brakes, the power of clutch, sorry, the throttle, okay, no? Everything is modelized by telemetry. So they tell you, you're braking too hard, too fast, too early, too late. And so it becomes a game between machine and man. and the best one is the one who gives the best interpretation of data. This is the story. So your answer is quite touching, because I don't know. Because probably if you put a guy coming from a great simulator into a serious machine, following the rules of the machine, probably it will go fast. Or it will go safe, because people racing is always looking for speed. But probably the target now of the great factories is safety, is not only, no? So, I don't know.
Shall I start? Okay. Hi, everybody. Thank you, Andrea, for inviting me. So it's a pleasure for me to be here. We will see how much of a pleasure is for Andrea after I finish my talk, because I have some surprises in store for you. And thank you, Marco, for the nice talk and the experience that you provided to this audience. So I titled my keynote here, "Where AI Meets Vehicle Dynamics." I'm by trade, so I got my Master of Science in Computer Science Engineering, but then I moved to electronic engineering, where I started studying control systems and automation control. Then I got my PhD in that area, and over time I kept my background in computer science, but I moved to control systems engineering. Then from there I started my academic career. I've been around a little bit, and then came back to Milano, where now I work on in the MOVE research group. It's a research group that is led by Professor Savaresi, and we do basically automation control in land vehicles. Everything that stems from the extremely low level, so Marco referred to actuators, so we do research in actuators, think about steer-by-wire, think about brake-by-wire. Those all are control systems that are designed to basically actuate and intervene on the dynamics of the vehicle. And from there, we move up to vehicle dynamics control, so classical stuff like ABS control, traction control, ESC, torque vectoring, up to the highest level that we have been working with recently, that is autonomous driving, and even higher fleet control. But today we will talk about, we are here after all for autonomous racing race, and we will be talking about that. So among other things, I'm a senior member of the PolimOve team. This is the team picture that we took at Indianapolis. You see the Dallara and then the team. Actually, you don't see me there because, unfortunately, for a series of reasons that have to do with COVID, I actually was never on the track with the rest of the team. But as Marco was pointing out, this is stuff for the young people. I may seem young, but I'm not that young anyway. So it's good that I was not there. So I supervised the team, but most of the credit goes to the guys that were at the racing track. And the race was organized last year. So actually the organization started 2 years ago, but the race happened last year. It happened a first race in October, where we ran and compete in Indianapolis. And the first race was basically the fastest lap. The team that could run along the racetrack the fastest won the $1 million prize. I won't tell you much about that because we crashed in that event. We were actually we were leading the race, but then a cable got unplugged in the car and we crashed. But what I will tell you something about is the second race that we have, and that is the one that I prefer, mostly because it's more interesting, and only secondly because we won. But that's actually the most interesting. That's why I like it the most. And the second race was in India, in Las Vegas, and it was a head-to-head race, similarly to what you're going to do in the coming days. So it was we had two cars on the racetrack, and it was a head-to-head race with one defender and one attacker that played to try and overtake one another at increasing speeds. So, okay. And this is the final part of the race. The green car is the Politecnico Milano team car. The blue car is the Munich Technical University. This is one of the last passes. This is the time that Munich took us. And then it was our turn. And here it comes. Actually, there should be also the audio, but probably the...
Accelerating onto the front stretch and a spin from Tomb down to the infield and able to continue.
And this is where this is when we won. And you could already tell that we won, or well, why do you think we won? What was the key point that made us win there? If you look at what happened, it was not really a problem, let me say, with perception. So the Munich team was probably, well, the car was probably aware of where we were. It was not a problem with planning. So the trajectory, the overtaking trajectory was planned correctly. What we think, of course, we don't have access to the competing team data, but we think it was a problem with vehicle dynamics. Because you see there, the car lost control by itself. Nothing else happened. So there, my point is, and I start to make my point, is that, yeah, our artificial intelligence is great, we need it, but at some point we have to face the reality that we are dealing with physical systems, that we are dealing with complex physical systems, and that we have to understand how they work. We cannot entirely hope that the machine learning algorithm will learn everything for us. We have to put the work in. And today I would like to try and convince you of this, and this is the point where Andrea might not like my message, because I know that according to your rules, you are forced to use deep learning and machine learning, and I will try today to make the point that that's fine, that's fun, but that's not enough. And to start and understanding why I'm going to make that point, and I like provocative talks, as you can tell, let's start from why we do self-driving autonomous racing. Well, we do autonomous racing because it's fun. Let's be sincere about it. So you are spending your weekend here, and you're not spending your weekend here because sooner or later you hope that the technology that you will develop during this week will save lives. That's a nice thing to think, but you're here to have fun and to compete one against the other. There's nothing wrong in being sincere about that. But nevertheless, it is also true that the technology that we are working with, the technology that we will play with, will have, hopefully an impact also on autonomous cars. And in order to understand that, we have to be aware of the differences between the two worlds, understand where they are similar and where they are different. And to do that, we have to understand the framework, the classical framework with which we solve the autonomous driving problem. And usually what we do is to divide the problem. It's a sort of we as engineers, we always and often do that. We divide the problem into simpler, at least seemingly simpler problems. In the autonomous driving, they are perception, so we need to be aware of what's around us. Then we have the optimization and planning, so that is the decision making. We have to decide where we want to go, how fast we want to go, and then we have to be sure that we are able to do what we decided to do. And on top of this slide, you see the high-level breakdown, and then on the top of the slide, on the bottom of the slide, we see all the different modules on the different topics. But before going into a little bit of details on one, let me ask you, okay, let's stay at the high level. Let's start with perception. Do you think that perception is more difficult in autonomous driving, so like commercial or consumer-grade autonomous driving, or in autonomous racing? How many of you think that it's more difficult in autonomous racing? How many of you think that it's more difficult in normal driving? Good, great, and I agree with you. It's definitely harder in self-driving cars. And why it's harder in self-driving cars? Well, because when you are racing on a highway, on a circuit, things like this don't happen. So you don't have to care about people crossing the street. You don't have to worry about dogs on the street, children on the street, and so on. So this is an advantage, if you think, if you will, about autonomous racing. So what the things that we learn in autonomous racing will not really be applicable in the self-driving cars. What about, well, there's the answer there, so let's go back to the motion control. What about motion control? Do you think that motion control is harder when we are doing autonomous racing or when we are doing self-driving cars? Well, you already seen the answer. It's more difficult when we do autonomous racing. Why is that? Well, first of all, we have to understand that motion control is the idea of exactly actuating and achieving what the motion planner decided to do. And things like this happen. So also, this is another example. This was the, no, this was not. So was the Euro? No, I don't remember actually. I don't think that it was Hawaii. I don't know why there's on the video there's the name. Anyway, if we go back, we see that also in this case, couldn't have been a problem with perception, couldn't be a problem with planning. Simply, the vehicle was accelerating too hard out of the corner, and it lose control of the motion of the vehicle. So the things that we learn in autonomous racing will definitely be useful also for self-driving cars. What about the final point, that is optimization and planning? Is it more difficult in autonomous driving, or is it more difficult in self-driving car, autonomous racing, or self-driving cars? Well, here the answer is a little bit tricky. It depends. It depends. It's different, because when we do autonomous racing, we have to deal with issues that are complex, but they are different from the issues that we have and the challenges that we have in self-driving cars. But I would argue that they are equally complex and equally difficult. So here, it's probably a nice topic to stop and focus on this specific topic. Now, of course, the thing that I mentioned you about the things that we learn about autonomous racing will be applicable also to self-driving cars, even if normally you think about a self-driving car driving in a city at low speed. Anyway, what could happen is that a self-driving car may need to face sudden and unknown conditions, like, for example, ice on the road, or they may need to perform an aggressive obstacle avoidance maneuver. And actually, there should be a video here. And this is a classic video that shows what happens when you lose control of a normal car. So this is not a racing car, but still the things that we have seen happening in the videos before may still happen also on a self-driving car. So that's the point. That's one of contact point where we have to learn. We can learn things in autonomous racing. We can have fun in autonomous racing, but we also can transfer part of that knowledge to self-driving cars. And then we come to the main message that I'm coming with to you tonight. That is that artificial intelligence alone will only take you so far in autonomous racing, and by extension, based on what we talked about in self-driving cars. And the reason is that vehicle dynamics is complex. Vehicle dynamics is complex, and as Marco pointed out, the conditions that we may be facing are subject to a great deal of variability. So machine learning may be great to learn racing on a given condition, but and this is a research topic, this is an open research topic, it's not always easy to generalize what the machine learning algorithm is learning. So it's easier, or at least it's helpful, if we add to this scenario also our understanding of the vehicle dynamics, understanding of control systems, which means model-based design, differential equations, control theory, and other hard stuff. That's something that we cannot escape from. That's a hard thing of life. I don't know about your background. I guess that most of you are computer scientists or computer enthusiasts. How many of you remember how a differential equation looked like? Well, any differential equation. Ordinary. Yeah, we can do, most of the time for vehicle dynamics we can do with ordinary differential equation. Unless you want to go to the tire modeling, accurate tire modeling where you have to go to partial differential equations. So let's try and use the time that we have left to see how this sort of reasoning applies to the global planning problem. So when we are doing racing, what do we need to solve in order to reach our objective? Well, the global planning consists in deciding the trajectory that our car wants to follow or should follow, knowing the map. So we assume to know the map, we assume that nobody else is on the track, so that simplifies the problem a little bit, and then we want to compute the fastest trajectory, so how we can go around the track the fastest as possible. Well, this seems an easy enough problem, but knowing the map is not enough. And also Marco hinted at this stuff earlier. Knowing the map is not enough because the vehicle itself has some limits, and we have to account for the limits that that vehicle is subject to. And here I listed some of them. So there are engine power limits. We may desire to accelerate, but the engine or the motor may not be powerful enough. Then we have the actuator dynamics, and this is something that is often neglected and maybe you will experience firsthand later tonight. And here it's an example of a steering angle. So here we have a steer-by-wire. It's an autonomous car. It's equipped with steer-by-wire. And we may decide that we want to go from 0 to 11 degrees of steering angle instantaneously because we want to avoid an obstacle there. The thing is that there's an actuator in between, and the actuator cannot teletransport the steering angle from 0 to 11 degrees in a matter of milliseconds. What happens is that it takes time, and that time is not negligible. So here you see it takes almost half a second for this steer-by-wire system to go from 0 to 11 degrees. And when we plan the trajectory, we have to account for that. And then there is the most complex, if you will, problem of all, that is the tire-road interaction. Tire-road interaction is a bad beast, so to say. It's bad because it's complex, we say non-linear, and we will understand in a second what we mean with non-linear, and is extremely time varying. It depends on the temperature, so when you start racing, your tires are cold, they don't perform as well as when they are heated a little bit. But then, after some time during the race, their friction, the ability to exert forces will drop because they wear down. And all that time variability is difficult to learn by trial and error. So we need the help of mathematical modeling and mathematical understanding. And one way, a simple way that we can start looking at the tire dynamics is through the concept of what we call the tire ellipse. The tire ellipse basically describes the maximum force that the tire can exert. And the maximum force that the tire can exert is in two directions, basically. We can think about the longitudinal force and the lateral force. And as you can see, without going into too many details on this plot, but you already see that there's a trade-off. The more longitudinal force that you have, the less lateral force you have. So on the left, we have the longitudinal force, so how fast we can accelerate, how hard we can accelerate, and on the right-hand side, we have the lateral force. Basically, how fast we can go around a corner, because If we have to go around a corner, we have to be sure to have enough lateral force to keep on track. And when we combine the lateral and longitudinal force, we get to the concept of the ggplot. The ggplot basically is the tire ellipse. It represents the tire ellipse, meaning that if we are going to accelerate, if we are accelerating straight, we can accelerate faster, we can accelerate harder than if we are both braking and accelerating. This is why usually when you go to driving school, they tell you, first you brake, and then you corner, then you turn. Because if you try to turn and brake at the same time, things get messy. And of course, racing, Marco and other racing pilots can manage that combined situation, so that trail braking, when you do the hard braking, then you start the corner while still braking, you reach the apex of the corner when you are constant speed, and then you accelerate out of the corner. And all these things are extremely important when you are doing racing, and we have to take them into account. And then on top of this, so these are basically what we call static limits. Static limits means that we can look at the behavior time by time, instant by instant. But then, if we want to make things even more complex, there are even more complex things, because there are also dynamic properties. So this is, for example, what happens when you apply a sinusoidal steering input at an increasing frequency. So you start very slowly, and then you accelerate your steering action. If everything was static and nice, we would expect the car to basically start turning, but faster and faster, but always with the same amplitude. In reality, that doesn't happen. So on the bottom plot, you see the yaw rate of the car, so how fast the car is turning around its vertical axis, and you see that that's far from being constant. Even if I'm not applying a greater steering angle here, the yaw rate here is larger. This is what we call a dynamic property. And these things are complex. These things are extremely complex to manage. Then we go back to the global planning. Am I good with time? Am I with time? Then we go back to the global planning. So now let's consider the things that the preliminary concepts that we have recalled, and try to understand how we can apply these concepts to designing our best trajectory. We have two ways of doing that. So we can either go the hard but optimal way, that is the dynamic way, or we can go the slightly easier way, that is the geometric way. The hard dynamic way means let's consider all those properties, the tire characteristic, the tire nonlinearities, the dynamic properties, the actuator dynamics. Let's write a model, and that model will be, as I referred, made of differential equations, and then let's try to optimize the trajectory based on that model. But there are ways and tools to do that. We don't have time to even scratch the surface of those methods today. But today, I'd like to talk to you a little bit about the geometric way, which is still interesting, which is still very important, because it still makes the bridge between the objective and the properties, the dynamical properties that we have to consider. The idea of the geometric is to basically split the problem in two. We first design the path, so just the sequence of points that I want to track on my track, and then I design the velocity. And then I try to go along that path at the fastest speed. Now, if you think about it, the two cannot be really separated, because if I want to go around a corner, the best trajectory may depend on the velocity and on the maximum acceleration that I can reach around that corner. So let's consider a little bit the problem a little bit more mathematically, but I'll try to keep the mathematical notation light enough. So the idea is that we have to go around the corner. We have to design the path that goes around the corner. And we want to design the path that takes the least amount of time possible, the fastest path. there are two extremes to this problem. We can either design the shortest path, that's intuitive enough, because the shortest path is the path that leads to the least possible space that I have to cover, so ideally that could be the fastest one. Or I could design the path with the least curvature. Why designing the path with the least curvature is beneficial? Well, because if I have a wide turn rather than a narrow corner, the lateral acceleration that I will feel around, going around that corner will be lower. And if the lateral acceleration is lower, I need lower tire force to maintain the trajectory. So the two things are that I may want to achieve are in opposition, because on one side I want to design the minimum path. But the minimum path, if you think about it, it's quite easy to understand intuitively. It's the one that goes around the corner, around the tightest corner. Whereas, so that's the path with the highest curvature. On the other hand, the corner with the path with the lowest curvature is the one that takes the wider turns, and which are also the longest path. It's also the longest path. So I need a way to balance these two things. And how can I do that? Well, I can set up what we call an optimization problem, for which I need to mathematically describe everything. We don't go into the details. Suffice to say that we can basically split the track into waypoints, and my optimization decision will be the points, so how far from the inner track bound I am at these waypoints. And my optimizer needs basically to decide each of these points altogether in order to either optimize the path, so the length, or either optimize the length, so curvature or length, sorry. Or we could be a little bit smarter and try to combine the two. So instead of focusing only on one or the other, we can try and focus on a combination of the two. And this is what this formula entails. So here we are trying to find the positions so to basically penalize both distance and curvature. And we have weights. We have to decide weights. So how much weight do we give to one and another? Well, it's too early to decide that. We have to, for now, accept that we have a weight. Then, after we decided that weight, we can actually solve the optimization problem. And here are some examples, of course, quite intuitive. If you think about the minimum curvature, you get the red curve, which is, you see, that takes that corner with the wider trajectory of the two. Or you can get the minimum length, which is the blue one, which stays close to the inner bounds of the track, because that's the best thing. So we have this tool in place that, given the weight and the weight between that I want to give between path, so length and curvature, it gives a trajectory, a path, and then the next thing is to decide how fast I want to go around that path. Very quickly, the idea, I'm running out of time, so let's consider this. The idea is to start from the apex. So we mentioned that at the apex, that's where the maximum curvature is, and that is where I want to give maximum lateral force, because there's no point in accelerating or braking at the apex. So that's a fixed point. Starting from that fixed point, I basically can accelerate as hard as I can. So I try to imagine what happens when I am accelerating out of the apex as hard as I can. But then, of course, I cannot keep on accelerating as hard as I can, because sooner or later I have to brake. And also, I have a limit on how hard I can brake. So I solve the problem in another pass. So first, I solve the forward pass. Imagine that I only need to accelerate. Then I solve the backward path. Imagine that I only need to brake. So I basically go back the path, step by step, and I imagine what happens when I'm braking at the highest performance. And this is basically what happens. So you see here, I'm accelerating and cornering, which means that I'm staying on the surface on the limit of the ggplot. Here is where I reach the straight, so I can accelerate the hardest, and then suddenly I jump to braking. And initially I brake the hardest because I'm going straight, and then I start the trail braking, so both braking and cornering. Then at this point, I have a way to optimize also the velocity, but I still don't have the final solution. The final solution consists in, now that I have every block in place, what I can do is to try different weights between the curvature and the path, and play around with different weights. I basically find the weight that gives me the best lap time. And as you can see here, the minimum curvature is the longest path, the minimum length is the shortest path. The optimal one is actually something in between, because it's for this track is 17 kilometers, and it takes 89 seconds instead of 90.4 seconds, that is minimum length. So you see that combining things will make things a little bit easier. So we can split the problem in two, and then we can combine the problem. And all of this is based on the understanding of the vehicle dynamics and understanding of the problem and the mathematical tools that we need to solve the problem. This is not the Indy Autonomous Challenge. This is the Robo Race. It's another competition that we are taking part of. This is instead of ovals, we run and we race on tracks. And this is, of course, the problem of the global trajectory. You have seen that it's already quite complex, but it's a simplified problem because it doesn't consider the fact that sooner or later we want to race against other people. And when we have to race against the other people, it's the same problem altogether, because we still have to consider the limits of our car in terms of road friction, in terms of vehicle dynamics, but also we have to consider the other vehicles and try to avoid them. So basically we are solving the same problem, but instead of solving the optimization problem beforehand, I need to solve it in real time. I need to solve things as things happen, which of course makes the things more difficult. And this is what happens in a race. The red car is the opponent. The green trajectory is the best trajectory. So you see that here we are off the best trajectory because there is an opponent. The blue one is the trajectory that we compute to overtake. And then we go back to the best trajectory. And we have to solve this online in real time. So just this brings us to the conclusion. The message that I came to you with today is that artificial intelligence is great, but it's not enough. It's not enough. We have to understand the dynamics that we are dealing with. And for that, we need to be able to formalize the objectives, understanding the objectives, and understanding how we can translate those objectives in mathematical requirements. And then, of course, it's not just about the static world, it's also about the dynamics. And I'll leave you with the final video that was shot this April. And this is when we beat the autonomous land speed record. Which may seem easy stuff because we are going straight, but hopefully the discussion that we just had has convinced you that it's not that easy, and also with the comments that Marco gave you about the difficulties of operating with open wheel car, going straight is not as easy as it seems. Okay, so thank you. good luck and have fun.
So Matteo taught us that software has limits, but I think our students are going to push them for this competition.
No, it's not software, it's artificial intelligence that has
Okay,
its
yeah.
limits.
Questions for Matteo?
Hello, thank you. So you say you believe that AI is not enough, which is fair and valid, but I guess you had the same belief like 5-10 years ago as well, that AI is not enough. But over these last 5-10 years, has there been a change in the certainty of your belief? Are you more confident or less confident right now about this?
Yeah, so of course the advantages in artificial intelligence during the past 5 years have been astonishing. Still, a problem, so you see that artificial intelligence is even able now to actually create art and stuff like that. The problem there, in my opinion, is that is the amount of data that you need to provide to the artificial intelligence in the training phase. And that is expensive. Providing data is extremely expensive, especially in autonomous racing. In autonomous racing, so when we were preparing for this race, we had access to the track probably 6-7 times, and that was all. And you can imagine that collecting enough data, especially when you are starting from scratch, because you don't have a way of driving that car manually, so that car doesn't have a cockpit, doesn't have a steering wheel, so we cannot drive it manually and then learn from an expert driver. And so the point is, artificial intelligence is great, but it needs data. It needs somebody who's capable of running the experiments and designing the experiments, because you have heard hundreds of instances where artificial intelligence was trained on faulty data or not so complete data. So I agree. I'm not saying that artificial intelligence is not useful. It's extremely useful. It's not the only tool in our toolbox that we have to focus on.
So thanks a lot for the nice presentation. So I have a question. So you've shown in an impressive way that there's still a lot that needs to be done in terms of modeling the car physically and also modeling the environment. But the way you showed it looks like it's mostly engineering and also scientific challenges which can be tackled, and in the next years they will be. So sometime in the future, autonomous racing will reach superhuman performance. And then what? I mean, what is the goal after that? Once you have superhuman autonomous racing, where do you go from there?
Well, learning to drive, no, but I was thinking about racing. So besides the impact that it has to do on the world, beside, it's a change of perspective. So of course, if you talk to a motorhead or somebody who's passionate about driving, they won't like this, because okay, what's the point of having computers racing against one another? But if you ask a computer engineer who's maybe not used to drive, that's where they have fun. So that's gonna be. So the fact that it's gonna be superhuman from the autonomous racing perspective, still it's not a problem for the computer engineers, because there will be competition between superhuman drivers. So one way of looking at it is this. Then of course there is all the problem of, will like lay people like the competition, will they watch it on TV? That I honestly don't know.
Matteo, thank you very much for your presentation. It was really very interesting because you were merging some empirical behavior with theoretical. And I especially like the second best or relative best line when you are on track with other lines, with other competitors. But I was asking you, and I connect with the question of the friend, how can the model take note of simple, very simple. I was looking your lines and your equation. Okay, great. But you are not talking about, for example, aerodynamic charge. You are not taking care of braking. You know that downforce is a function, a cubic function of speed. So you know that you have to bring the maximum speed into the cornering, because otherwise you lose downforce too early. So you have to bring the maximum speed into cornering, and then sometimes you brake even in corner just to move the weight in front to have even more cornering. So how can you take care of all this stuff which is made by empirical learning? I mean, sometimes I drive straight in the corner, straight, and you say, but you're going out. But I bring the maximum speed straight, and then at the lowest speed I turn cornering. I mean, I'm serious. Close angle, no? And then I push full throttle again, like it was a serious corner, not a curve. And how can you take, exactly, how can you take care of all this stuff, even with the pressure of tires, the temperature? I thought that machine intelligence, artificial intelligence, was more effective than myself, because it can take with sensor all the information around the car in all the body, in all the frame, no? While I don't. Sometimes I lose control because I don't think about the temperature of sorry, thank you very much.
Thanks for the question. So here, of course, tonight, I tried, and even in this case, the time was not enough to really be clear about everything. I used a simplified model. And I stressed the idea of a static model. So these are static limit. Then what happens, as you pointed out, is that in reality, these limits will change because the tire changes the temperature. Not only that, there is load transfer. And load transfer basically means that the size of this limit depends on the acceleration itself. Because the more you are accelerating, the more you are loading the rear tires. So this changes in time. And the way in which we can take care of this is with two ways. One is basically make the approach that I described tonight more complex. So we have the mathematical models that describe all those phenomena. So there are the equations. We have the equations. We have a pretty good understanding of how the tire force changes with temperature, how the tire force changes with pressure. Some of them are, we call first principles, so they are first principle models that they are derived from basic physics. Some of them are empirical models, in the sense that we put the tires on a rolling bench and we perform experiments. But we have the models for them. We have the models, and then we can, by using optimization algorithms, find the best strategy based on that model. The other approach is the machine learning approach. The machine learning approach forgets about model. The machine learning approach doesn't care about models, it cares about experience. Because it learns from experience, basically. It learns from data. And when you are going aggressively, so when you try the maneuvers that you have done, so either we train the machine to learn from you, and I trust that you are very good, but there's no proof that you are the best. So if the machine learns from you, it may be learning something that is not optimal. But still, it can be done. Or we let the machine, you have seen Andrea referred about reinforcement learning, you let the machine learn by itself. That's an option. That's an option that theoretically it has the possibility of actually be able to find the real best optimal, an optimal that is so counterintuitive that no human driver will ever try it. The problem is that you have to try it. You have to run the car and learn what happens. And that's risky, that's dangerous, and that's expensive. Even if it's not dangerous, because we are doing with autonomous racing and nobody gets hurt, it's extremely expensive. I won't tell you how much it cost. The time that we crashed the car costed us. So I don't know if that answered your point.
Okay. Yeah. one question regarding, a more practical question regarding the movement on the ellipsis, which you showed. I was really interested in the, basically we have the constant acceleration with the maximum speed, we change, reach the maximum and then goes down again.
Yeah.
I was curious regarding how it optimizes in a sense, in the physical sense, to have maximum acceleration, so a constant, then after reaching until reaching the maximum velocity, and then already goes down, or reaching before, because it's a matter of movement basically, reaching before the maximum speed, using that to your advantage, and then using the down acceleration basically.
So the point here is that it's a this is also called it's a theoretical result that is known as bang-bang control. It actually can be mathematically proven that when your actuation is saturated, the best thing that you can do under some assumptions and some hypotheses is to always stay on the saturation of your actuation. So either you are accelerating the hardest or you are braking the hardest. And so here, basically what happens is that you pointed out that we could be accelerating harder. Yeah, if that was possible, we would be doing that. But here, the mechanism is such that at each time instance, we are accelerating at the maximum acceleration that we can achieve given the tire constraints, the engine constraints, and the aerodynamic if we consider a more complex model.
And also because it considers the displacement, so the movement, not only the acceleration itself.
Yeah.
So how can you basically manage the ratio between going in displacement and using the max acceleration?
So if I understand your question correctly, the displacement, what you call displacement, is actually managed at the later on. So remember, I went very quickly, so the idea is that, first of all, we learn how to plan the path, assuming that we have somebody that tells us how much we want to balance curvature and length. So we have that tool. Then we have a tool that, given a path, it runs along that path with the maximum velocity. But that doesn't mean that that path is optimal. It only means that we have a way to run around that path with the optimal velocity. And then the final step is to bring them together. We bring them together, we try basically a bunch of different combinations between curvature and length. For each of those, we compute the fastest way of going around that path, and then we look at the combination of the two that gives the best lap time. So the displacement is considered in this, we call it outer optimization loop.
Thank you, Matteo. So let's thank the speakers again. Cool.